In the last video, we went over the first of our electrophilic addition reactions to alkenes. Remember, in this section we looked at the addition of hydrogen halides like HCl or HBr or HHI. And we found out that these reactions proceed all in the same way, through the same pathway, involving protonation of an alkene to form a carbocation, and that carbocation reacts with a halide. We've learned about their mechanisms, we've learned how to predict their products, and we've learned about the stabilities of their intermediates. We also saw some interesting pathways involving what we called 1,2 hydride shifts, or 1,2 alkyl shifts. And these were reaction steps which would allow a carbocation to shift to a more stable, even more stable carbocation. Alright, so we're going to apply what we learned in that last video to a new reaction, a related reaction though, and that involves the addition of water to an alkene. Okay, so we're adding water just like when we add our water to our bodies. We call this a hydration. Alright, in the hydration reaction, if we just mix water here with an alkene, what happens? Nothing. No reaction. Okay? And in fact, this is kind of lucky because we have lots of alkenes in our bodies. We have unsaturated fats, which are important in our membranes. And if hydration reactions happen spontaneously, then all of those double bonds in our body would all become hydrated, and those compounds couldn't play the role that they need to. Alright, so let's look at how we can actually make this reaction take place. So what we need is to add a catalyst. Alright, and remember, a catalyst lowers the activation barrier for the reaction. So what we're going to add this time is some acid. Okay, most commonly, probably the most common acid for this is sulfuric acid. We usually won't designate the specific acid, but we can use H+, or we know that if we put a strong acid in water, what do we get? We get H3O+, which is hydronium ion. Alright. So with hydronium ion, or a strong acid, we can get a hydration reaction to take place. So let's draw these H's in. Get an H here, those are the ones we started with. And now, just like when we added HBr, we add an H to one side, and we're going to add an OH to the other side. So if we compare this to what we learned before we had X, where X is a halogen. Now we have OH. So this whole OH group is going to play the same role as the X group did in the previous reaction. Alright, so our first step here is for the double bond to get protonated just like it was before. Okay, I didn't really draw this right. We should have a bond between the H and the O, and that's going to break. And what are we going to form? We're going to form a carbocation intermediate, just like we did before. So we protonate there, we have an H here, and a plus. Alright, so we form a carbocation. That carbocation can react with a nucleophile. In the past reaction, the nucleophile was bromide or chloride. In this case, the nucleophile is going to be a water molecule. Alright, so water molecule, remember, has 2 pairs of non-bonding electrons on the oxygen, and those, the delta plus there, can be attracted to the plus of the carbocation. Okay, does that get us right to the product? Well, not quite. We've got one more step to do. Alright, we have our 2 H's. We added this H here, and we added water. So our water molecule is still intact. Alright, and we had the plus before on the carbon. Where does the plus go now? So the plus will go on the oxygen. So oxygen, when it has 3 single bonds and a non-bonding pair of electrons, will have a plus charge. You can calculate the formal charge of that if you want. Alright, and so then in the last step, we just need to remove one of the protons on that oxygen. Alright, so we're going to use another water molecule to do this. So this is going to come in here and take off that H. Right, that's going to give us our product. And this water molecule, is, when it picks up its H, is going to form hydronium ion, and that hydronium ion that's formed here can go back over here and react with another alkene. Right? So there's a catalyst, it's getting consumed, but it's getting regenerated over here, so it's never completely used up in the reaction. Okay, so why is it that this bottom reaction works when we add acid, but it doesn't work without the acid? Alright, we can understand this by thinking about the first step of the reaction. Alright, so the first step has the alkene getting protonated. Alright, so if we look up at the top one, the alkene is the same, but we have water. So we have a difference in water here, in acid. So up here, water is just not a strong enough acid to protonate an alkene. Or we could say it the other way, is that the alkene is quite a weak base, and so we need a strong acid to react with it. Okay, so without the catalyst, no reaction takes place. But if we add the acid catalyst, then we can get this hydration to take place. So we can call this an acid-catalyzed addition of water, an acid-catalyzed hydration reaction. Alright, so let's look at some other examples. Alright, so these are going to proceed just like what we saw for the addition of HX. So we can mostly just go straight to our products. They're going to follow Markovnikov's rule, and so the H is going to go to the less substituted side, the OH to the more substituted side. Right? So we get this product, this tertiary alcohol. We do it on the next one. Again, the H will go to the less substituted position up here, OH to the more substituted position. So we get a methyl group here and an OH here. Okay, what about the next one? What if I said that we get this is the product? Right? We know how that forms, right? Remember that this, let's redo that. We'll just protonate with the acid over here. We protonate on the end, so we get the secondary carbocation. And remember what happens here. We have a secondary carbocation with a highly substituted position adjacent to it. So we can get a 1,2 hydride shift. Not hydride, but a methyl shift, an alkyl shift, to form this tertiary alcohol. 1,2 alkyl shift. All right, so then that can react with water. All right, don't follow the trap of just trying to use hydroxide here, okay? Hydroxide doesn't work here because we're under acidic conditions, and a strong base like hydroxide can't form in acidic conditions. So we have to use water each time. Okay, so we attach our water molecule here. The plus charge on the oxygen. And then we have one more step where we use a water molecule, which does an acid-base reaction with that to form our alcohol plus hydronium ion. All right? So the key thing here is we form a carbocation. It doesn't matter if it's an addition of HX or the addition of water. If we're forming a carbocation, then hydride and alkyl shifts can take place. All right, so let's look at a related reaction. This is not really a hydration, but we're going to add an alcohol instead. All right, so we're going to relate this to the reactions we've done already. So first we started with HX, right? And then we did HOH. So in this case, all we're going to do is HO. We're going to have a methyl group in this one, but could it be other alkyl groups as well? So OCH3. So we're going to add H to one side, OCH3 to the other side. All right, so we can just predict the product, follows Markovnikov's rule. We put the H out on the end, and we get OCH3 right here. All right, so let's just draw this out. So remember, first, these two would react together, and we'd protonate that alcohol like this. Okay, notice that that looks very similar to hydronium ion, right? The only difference is we've got a methyl group here versus an H. Okay, so the first step then is going to be to protonate that alkene, just like we did before. To give us a tertiary carbocation. Right? We put the H over here. Right here, I can draw that in red if you'd like. All right? In the second step, the alcohol is going to react with the carbocation just like water did in the previous reaction. All right, this oxygen has two non-bonding pairs of electrons. It attacks here. Add this alcohol, but remember we have to keep that intact, right? So we get this is called an oxonium ion. It's an ion with the charge on the oxygen. And then what we have to do is deprotonate that to get to our product, right? And in this case, we can just use another alcohol molecule. This is going to come down. Acid-base chemistry, you're going to remove that proton. We get our product, and we form this protonated alcohol, right? And this can go back over here to react with another alkene. So notice this is following just the same mechanism. The only difference is that now that our nucleophile is neutral instead of with a minus charge, we end up with one more step in our reaction. We just have an acid-based step to give us our final product. Don't you remember me telling you when we were talking about acid-base chemistry that we'll see it often throughout this class? So when we see it here, we should just go, oh, that's only acid-base chemistry. We know how to do that, right? Straightforward and simple. All right, so let's look at some reactions where we're adding an alcohol and just predicting the products. Okay, so again, we're always going to draw the same carbon skeleton to start here. The methyl group, look at this is our whole alcohol here, so we're using an isopropyl alcohol or isopropanol. So we have the oxygen, and there's the isopropyl group. Okay. The next one, right, we're just going to add the alcohol here. We used propanol, so we get that product. What about the next one? Okay, do we just get the same thing? In this case, we get OCH3, is that right? No, that one's not right. Why is that? Because when we form our carbocation, we have this more highly substituted center next to it. So we can get a 1,2 hydride shift. Okay, so our actual product is going to be this one with our OCH3 like this. All right, what about the next one? Look at that structure. We have the alkene and the alcohol. This time they're in the same molecule. All right, so we can get actually what we call an intramolecular reaction. Okay, intramolecular. So what happens is, just like the previous reactions, the pi bond gets protonated to form a carbocation. All right, it's going to protonate on the less substituted side to give us the more stable carbocation. And so we get this tertiary carbocation here. Now, just like the reactions above, the alcohol can react with the carbocation. So this reaction, it just reaches around and reacts with itself. So it's like biting its own tail or something like that. And so we can figure out what size of ring it's going to make if we count this. 1, 2, 3, 4, 5, 6. So we're going to have a ring with 6 atoms in it. And it's going to have an oxygen in the ring. So we're going to have something like this. Like this. The oxygen still has an H on it. And notice that the position where the carbocation is has 2 CH3s, and that's going to be on a position next to the oxygen. Okay, so we're going to have 2 CH3s here. All right, so then this reaction would finish up just like the other ones. We're going to lose an H+, probably just the alcohol here, or another alkene would pull that proton off, and we would get this product here, which is a cyclic ether. Notice that in all of these, when we use an alcohol as the reactant, we have ethers as products. All right, this is an ether as well. It's just in a ring. Okay, so we're going to look at one more way to do hydration reactions. Okay, this second approach is called a hydroboration-oxidation reaction. Okay, so it's going to use boron, hydroboration. So in fact, it uses BH3. Okay, so BH3 is called borane. Oops. Borane. Okay, other things in this reaction, THF is a solvent. It's called tetrahydrofolate. furan. Okay, and its structure is like this. It's a cyclic ether, almost like what we just saw. It has a 5-membered ring, and the name comes from furan. This molecule here is actually an aromatic compound. So right here is called furan. Tetrahydrofuran has 4 more hydrogens, right? Okay, so that's just a solvent. Okay, the other things, this is hydrogen peroxide, hydrogen peroxide, and then we know everything else. Okay, notice how this is written as 1 and 2. So that means that this is a stepwise reaction. Okay, we have step 1. Right, we have to do the first step, and once that first step is done, then we can add the reagents for the second step. Okay, we can't just add those all together or it won't work. Alright, so let's compare these two reactions. Alright, so the first one is just the acid-catalyzed hydration. Okay, so we know we're going to, let's add these in here. We know we're going to add an H to one side and an OH to the other side. Okay, so if we start with cyclohexene, we get this secondary alcohol. Alright, if we do the hydroboration-oxidation, we get this product. Is that different? No, look, those are just the same. This is dumb. Why do we have to learn a new reaction when it just gives us the same thing? Well, it's the same if we have a symmetrical alkene like this. Okay, the difference is going to show up when we have an unsubstituted alkene. All right? So here we go. 1-methyl cyclohexene. If we do our acid-catalyzed hydration, we know that it will follow Markovnikov addition, which means that the OH is going to go to the more substituted side. Right? So the H would go to the less substituted, the OH would go to the more substituted. All right? So when we do the hydroboration-oxidation, watch this. This product gives us this. Dang, look at the OH is in the opposite position. So this one we sometimes call anti-Markovnikov. Okay, so it means that the H goes to the more substituted end, and the OH goes, to the less substituted side. Right, so this is just backwards. And so these reactions, like we said before, these reactions are what we call regioselective. Right, because there's really two possibilities, right? We could have the OH either here, like we do here, or at this position, but this reaction selects for this region for the OH, and this reaction selects for the other region. All right, so they're regioselective reactions. All right, so how does this take place? All right, so if we just start with 1-propene, we know that if we just do the acid-catalyzed hydration, we will get isopropanol. Okay? If we do the hydroboration-oxidation reaction, then what will we get? Then we will get 1-propene. Okay? So let's take a look at this step. So this is kind of how it works. Okay, so here's our alkene, and borane reacts with it like this. Okay, so again, let's think about borane first. I'm going to write it out here. Okay, for borane, it's different than most of the other things we've looked at, is it has some polarized bonds, but it turns out that the boron is the more electropositive element. So we have a delta plus on the boron and a delta minus on the hydrogen. Okay, so when the pi bond reacts with an electrophile, you know, in the past it always reacted with a proton, but when it reacts with an electrophile now, it's going to react with the boron side. Okay? Now, it doesn't, in this case, really form a carbocation, but this hydrogen with its electrons comes down at the same time. Okay, so this is what we call a concerted reaction. Okay, and what this means is that all bond forming and bond breaking happen simultaneously. Alright, so we don't form another intermediate. So if it did that, then what we would get is we would get this species. We'd get, let's draw in our first H there. We'd have two H's here. We'd have two H's here, right, because this is CH2. And we'd have BH2. Okay? Now, because the boron still has two hydrogens, it can react two more times. Okay, so I'm going to just do it like this for right now. So it's going to react with 2 times more of these alkenes. So it's going to form this species here. Okay, so there's our boron, and it's going to have 3 propyl groups attached. Like this. Okay? So it's done at 3 hydroboration steps. Now what happens to get to our product is that we have to do the second step of this. We add hydrogen peroxide, hydroxide, and some water. Okay, this is the oxidation step. And so actually what we get for every one of these species, we'd get 3 propanol molecules. All right? So because borane can deliver 3 hydrogens, sometimes it's a little confusing, or it doesn't really work as well if we need 3 times this to 1 times that. If we want to control the amount of boron hydrogen bonds, sometimes we use other reagents instead of boron, like this one here. It's called 9-BBN, and notice it only has 1 boron hydrogen bond. The other thing is that because this part of the ring is very bulky, it really favors putting this group, that would be the bulky part, to the less substituted side. Okay, that would help this regioselectivity. Okay, the reason that we can see now here is, for one thing, is steric strain. Okay, the other thing is if we draw out what might look like the transition state. Okay, so we're breaking this bond. We're forming our bond to the boron. Okay, we're breaking the bond to the hydrogen, and we're forming this one. Okay, so in this process, if we start forming the bond to boron first, we're going to end up with a delta plus at this position. Okay, it doesn't form a full carbocation, but we form some delta plus, and so that delta plus is more stable when it's at the more substituted side. All right, so I'd like you to know kind of the mechanism for this first part of the reaction, but we won't really mechanism for this second part. Okay, so let's look at the oxidation step. So this part is what we already talked about. And we got this trialkyl borane here. We'll call that trialkyl. Let's try if we can spell that. There. All right, so what essentially happens is that we add a hydrogen peroxide molecule into each one of these boron-carbon bonds. All right, and so we can see them right here. See H2O2 right here and right here. All right, so we generate we consume 3 hydrogen peroxide molecules. We get this compound here, which is called boronic acid, and we get 3 alcohols. Okay? So the important part of this, though, really, is that this hydroboration-oxidation reaction is just an anti-Markovnikov hydration reaction. Okay, so we're adding water, but we're adding the H to the more substituted side and the OH to the less substituted side. So the regioselectivity is just reversed compared to the acid-catalyzed. All right, so there's our hydration. We added water. We also added alcohols. We saw that in the hydration and in adding alcohol, we proceeded through carbocations just like we had seen before. So the mechanism was almost identical to what we saw when we added HX. All right, in the next video, what we're going to do is we're going to look at the addition of just halogens, so X2, and we're going to look at a reaction called catalytic hydrogenation, which we add H2.